Okay, well, thanks everyone for coming along to now the fourth lecture of this week on model-based derivative-free optimization. So you finished hearing from me, fortunately for you, and now today we're lucky to have with us Professor Zaikun Zhang. He's currently in the US, but Zaikun is a professor at the School of Mathematics at Sun Yat-sen University in China. He got his PhD from the Chinese Academy of Sciences. He had postdocs at the University of Coimbra and in Toulouse, working with people in derivative-free optimization. He then had a continuing position at Hong Kong Polytechnic University. So Zaikun does a lot of work on derivative-free optimization methods, both model-based and direct search, two of kind of the biggest, at least local DFO methods. And within this area, he's made a lot of advances. Going to highlight in particular, he's done a lot of work on probabilistic direct search methods, which is a great way to improve the scalability of those techniques by introducing randomization. He's also done a lot of work on subspace methods, and again, looking at large scale methods for model-based DFO, which I think he'll be talking a bit about today. And I did flag yesterday as well. Zaikun has done a lot of work in model-based DFO software, particularly looking after the work of Mike Powell's software that I mentioned yesterday. And he's got this excellent package Prima on his GitHub, where he's sort of got the new and improved versions of all that code, which I think was 3 or 4 years of very intensive work. So he's probably the most knowledgeable person on those bits of software in the world, I would say right now. Anyway, so we're very happy to have Zaikun join us. And Zaikun, I'll pass it over to you. Thank you very much.
Okay, great. Yeah. I think good morning, and also in case you are also in the evening, in US, good evening to everyone. And thank Dimitri and Lyndon for this wonderful uh, organization and the invitation. I'm really honored and also, in fact, humbled to be here to give this talk on model-based and subspace derivative-free optimization after Lyndon, because Lyndon is really expert on model-based and also subspace methods. And also, I feel lucky to give this talk after him because even though I didn't come online during the Lyndon's lectures, but I did had a look at the YouTube video and also the slides. I think so. My work has been will become very easy after Lyndon's very systematic review on these methods, especially on model-based methods. So today, the title of my talk is I have two titles. The first one is a bit mysterious maybe. I call it Power, Yuan Dual, and Optimist. And then there is another title is model-based and subspace derivative-free optimization algorithms. So let's start. So before starting, I'd like to echo what Linda mentioned. In fact, I work on both model-based and direct search methods. And with my PhD student, Huang Tunxin, in Hong Kong Polytechnic, we have a recent paper on some analysis on probabilistic direct search method. I will not talk about today, but I'd like to emphasize that this is a theoretical piece of work. What I'm going to talk about today is more on algorithms and software, but I do work on also some theoretical aspect of DFO. So if you are interested in our theoretical work, you're welcome to have a look at this archive paper. So this part I think I can skim very quickly. So we are interested in solving optimization problem without using first order information. So only based on function values. And these problems come from, for example, simulation-based problems or problems where we can theoretically we can have the first order information, but maybe the first order information is too expensive or sometimes not reliably available due to, for example, noise. And our basic assumption that is that we can evaluate the objective function, but the objective function is often quite expensive to evaluate, and also very often the values are noisy. So our purpose or our goal is to minimize or reduce this objective function using as few function values as possible. And yeah, we can have unconstrained, but sometimes we also have constraint problems where the constraints are also cannot provide further information. So there are many classical algorithms. I suppose Lyndon has introduced many of them. So here I give you another three examples. Meet is probably it is one of the most widely used optimization algorithms. Not only derivative-free optimization algorithm, is because this algorithm is quite simple and easy to understand. So it's quite popular among engineers. And also there are powers algorithms which are model-based, and I will talk about them more in later part of this talk. And also SolNP plus is in fact it's a very interesting algorithm. It is also quite old. It was first invented by Professor Yin Ye, Chinese American applied mathematician, quite famous in the OI Society, and he did it in the 80s, I think. And then he didn't continue to work on DFO, and then very recently, 2 or 3 years ago, he and his students developed this algorithm into a quite good piece of software, in fact. My motivation or inspiration of working on DFO came from the late Professor Power, and I believe that Lyndon has mentioned about his work many times in his lectures. So Professor Power once recalled why he worked on this kind of algorithms, optimization without using derivatives. He said that he started writing optimization programs in Fortran in 1962 when he was working in Harvard. And then he moved to Cambridge in the 70s, and he became a consultant for MSL, and he contributed many code, a lot of software packages to MSL. One of them was Tau-Min. This is algorithm that solve linearly constrained problems using derivatives. But the customers of MSL prefer methods that do not need derivatives. So MSL forced Power's software, Tau-Min, to employ finite difference to approximate the derivatives. And Power said very clearly in his this was a piece of paper. In fact, in his paper that he was not happy, and this was his motivation to work on derivative-free optimization. And yeah, I think Power's first work on derivative-free optimization was in fact his second paper in optimization. His first paper was on DFP, of course, very famous. And the second one was conjugated direction method, a method that does not use derivatives but construct conjugate directions to do line search. But it is not one of the methods that I will talk about today. As Linda mentioned, I did my PhD thesis in Chinese accounting sciences, and my supervisor was, in fact, one of Power's former PhD students, Professor Yat-sen Yuan. And Professor Yuan is in fact, I think, the earliest person studied derivative-free optimization in China. In fact, his first NSFC grant proposal was on derivative-free optimization. Back then, he called it direct methods for nonlinear programming. And this was very soon after he graduated, not graduated, after he left Cambridge to China, and he started working on duty-free operation as one of his topics. Um, of course, I'm sure that Lyndon already mentioned applications of the free operation. Here, I just list a few more references, and I'd like to emphasize that these kind of problems, this is also appear in machine learning and in AI. For example, one of the problems in AI is to do fine tuning for large language models. In this case, in theory, you can do backward propagation to get the first order information, but that is quite expensive in terms of memory. So people are talking about whether it is possible to avoid backward propagation and use only zeroth order or function values to tune the large language models. Of course, these problems are huge, and the methods that we will talk about today are not designed for these kind of problems, or they are not they cannot solve directly these kind of problems. But after I believe that combining them with some kind of low rank approximation method or subspace methods, uh, there may be a hope to also at least approach these kind of problems. Uh, and here I list a bunch of monographs and surveys on duty-free operation. And the first one, the most recent one that I know is, of course, from Linden, is Introduction to Model-Based Duty-Free Operation. And also, when I was working at the Hong Kong Polytechnic University, I my first PhD student there, Tom Hagono, also wrote a thesis on model-based DFO, and it also provide at least in the first chapter, it provides a survey for this area. And then there are also some classical references like, yeah, I think 2019, maybe we don't call it classical yet, but it's also a very good survey by our friends Jeffrey Larson and Matt and Stephen. And then there are two monographs, one by Charlie Audet and Warren Hare, Digital Free and the Black Box Authentication. And another one, I think we can call it classical. It is from Andy Cohn, Katja Sandberg, and Luis Nunes Vicente, Introduction to Digital Free Authentication. And also there are other surveys. I think I believe that Lina also mentioned this. Here we talk about the duty-free authentication or authentication that does not use first order information. The reason is not normally it is not because the problems are non-smooth. If the problems are non-smooth, then we should ask the non-smooth authentication experts about non-smooth authentication methods. Here, we do not use derivatives, or more generally, we don't use first order information. It's because we don't have access to that information. And also, people also talk about black box authentication. And it's because a lot of derivative-free authentication problems, they are defined by some kind of black box where we do not have formulas for the objective function. But the real problems in practice, they are often gray boxes instead of black boxes. If we have any structure that we can use, then we should use them. Otherwise, it's not likely that we can solve the problem in the best way. The same is that if we have any kind of first order information, even though the first order information is approximate or is not always available, then as long as we have some kind of this kind of first order information, we should use it. Otherwise, it's like to fight without using your hands. Is very unlikely that you can solve the problem to the best. But in the following discussion, I will be lazy just to assume that our problem is pure black box. There's no structure to exploit, and also there's no not any kind of personal information that we can exploit. So everything that we have is just first zeroth order information of function values. So this is an outline of my following discussions. So I will start with power. Lyndon must have also mentioned. So power in his about 30 years, no, not 30 years, more than 20 years of working on DFO, he developed 5 DFO algorithms. All of them are model-based. And also for each of them, he coded it very carefully into open source software. Here I list all the titles of these algorithms, and also particularly 2 things. First, the models that were used in the algorithms, and also the days that the code was released, and also the paper was published. Of course, for the models, there were 2 kinds of models, or 3 kinds of. Cobila, the earliest one, was using linear models or linear approximations for the arithmetic and constraints. And then later, he studied quadratic models. But there are 2 types of quadratic models. UBRQA was using the fully determined quadratic models, which means that he used interpolation to determine the model, and the system of the interpolation is a fully determined linear system, or the number of interpolation points was the same as the degree of freedom in the models. And then the later 3, UUA, BUVRQA, and LINQA, they were all underdetermined interpolation models, which means that the number of interpolation points in each interpolation system is much less or much fewer than the number of degrees of freedom in the models. And then for the, I also would like to talk about the date or the days when he released the code and published the paper, because as you can see, the pattern is quite different from what we do now. So he first released the code, and then, of course, when he was writing the code, he was also writing the paper, but he first released the code and then submitted the paper. And then after 1 or 2 years, the paper was published. I'd like to mention that for me, this means Powell was very, very extremely careful about the code. He didn't want to just write some paper and supplement the paper with a piece of very carefully written code. No, that was not his style. The code was at least as important as the paper, or maybe even more important. And then I briefly review how this model-based, especially interpolation model-based transfusion DFO work. So basically, it's a DFO method. So at each iteration, we build a model MK around the current iterate. Normally, this MK is built using interpolations, and then we do roughly speaking, we do classical transfusion. So we minimize this model to get a new trial point, and then we decide whether everything works well or not. If yes, we accept this trial point as our next iterate and increase the transfusion radius. Otherwise, we decrease the transfusion radius. But there is something that is very important that is hidden here. It is how to build the model and how to revise the model when, for example, when you find that things work well, or when you find that things do not work well. So I'm sure that Lyndon has talked about the details. Here, I will not go into the details, but we'll just show you a flowchart that is that was by Power. So he used this flowchart to describe his New A algorithm. So which is exactly a trust region interpolation model based DFO algorithm. You can see that this flowchart is not quite simple. It's not as simple as the classical first order methods that we often read in papers. So here we have, I think, 13 blocks, and each block is when you implement them, it is one or two subroutines, and the blocks or the subroutines, in fact, they are interconnected. And I think the building of the model and the maintenance of the model appears in at least two blocks in this flowchart. I think in block 5, yes, you will. It says that if move is bigger than 0, then Q is modified by some subroutine. So this is one thing. This is one place. I'm sure that there is another place where the model is also revised. So as we can see, these kind of methods are quite complicated. In fact, it's not only us that we find the models, these kind of algorithms are complicated. In fact, Powell in his paper, he also mentioned that the develop of this algorithm took him 3 years, and it was 3 years that were quite frustrating. I don't think it's very common that you read these kind of sentences in a paper, especially a paper from a great mathematician like Powell. So this sentence, I think, at least convinces me that even for Powell, this algorithm was complicated. So why these kind of algorithms are so complicated? When I was when I and my first PhD student Tom, we were working on these kind of methods, we asked us this question, and our conclusion, of course, is a very informal conclusion, is that it's because in this model-based DFO algorithms, there are two lines in parallel. One line is explicit. It is the optimization process. Another line, it is implicit. It is the model management. And these two lines, of course, the ultimate goal of these two lines are the same. So the model management process is to serve the optimization process. And finally, we hope to solve our optimization problem. But practically, when you look at the two lines, they don't always they sometimes they conflict with each other or inhibit each other. The reason is that if you look at the optimization process, if this process works quite well, then you can imagine that for a few iterations, the iterates may fall roughly or approximately fall into a low dimensional manifold. But then at the same time, if you look at the model management process, because we in these kind of problems, the function values are so expensive, so we normally we don't sample points particularly for the models. We use the current or the existing iterates to do the interpolation to get the models. And since, as we said, the recent iterates, if they work well, the roughly or approximately fall into a low dimensional manifold. And if you interpolate on these points, then you will have a very ill-conditioned interpolation system, which will not give you a very good model. And so that is why from time to time in these methods, you need to have model improvement steps to improve the geometry of the interpolation sets and improve the quality of the models. I suppose Lyndon has talked a lot about this in his lectures. With these two lines coupled with each other, this increases considerably the complexity of these kind of methods. Here, the complexity, I don't mean the complexity to get approximate solution. I mean the complexity of implementing these methods or even describing these methods. Despite of this complexity, Howard implemented all of his 5 methods into publicly available software, and the solvers were widely used in science and engineering. For example, when I was working in Toulouse, I had some connections with Airbus, and they have been using Power's solvers, especially Cobila, to design aircrafts. And within academia, these solvers are often used as benchmarks when designing new algorithms, even though these algorithms are already quite old. For example, the first one, Cobila, was designed in the 90s, almost more than 35 years ago. And the most recent one, Lincoln A, was designed in 2013, already 13 years. But still, they are quite good solvers, and people often use them as benchmarks. But however, if we look at the implementation, we will find that the implementation was quite classic. So the style was quite unique. It was all of them were implemented in Fortran 77, and with plenty of go-tos. And Lyndon knows this quite well because I think in Lyndon's PhD thesis, part of his thesis or a very important work was to work on a modernized version of POBRQA. So if you look at the original implementation by Power, it was not easy. It's not easy to understand, particularly due to the go-tos. This is not a surprise if you recall that, in fact, Power was one of the earliest users of Fortran. Right? As I mentioned at the very beginning of this talk, Power studied coding in the 60s, and Fortran was invented, I think, in late 50s. So Power was really the earliest users, one of the earliest users, and his style evolved with Fortran, but finally it somehow stopped at the style of Fortran 77. So his code is quite with a quite unique style. So that is why during COVID, in fact, I decided I must work on a modernized implementation. But you may ask, why should I work on this implementation? If these solvers are so useful, then one day, sooner or later, there will be some modernized version. Why should I work on it? This is, in fact, a personal commitment to Professor Power. Before he passed, he sent me an email asking me to look after his optimization software, especially this DFO optimization software. And so I promised to him that as long as I'm still here, I will make sure that his code is well maintained and will be continued to be used. And then some other questions naturally arise. For example, first, this seems to be a job for engineer or for engineers, right? But recall that I worked on this during COVID, which means I started 2020, early 2020, so 6 years ago. So at that time, there was no such AI tools. So we recall that Power, even himself, for example, first we have 5 pieces of code, 5 algorithms, and even for himself, for one algorithm. He spent 3 years on it. Of course, not only to implement it, but to design the algorithm and then implement the code. But if we look for an engineer to work on this, then this engineer would need to study the algorithms from scratch and then implement them in a reasonable amount of time. It's not an easy job. And even if I can find such an engineer and I hire him or her as a student or as a postdoc, how could I persuade this person to be fully devoted to this project for maybe 3 to 5 years, but without producing a single publication? Because working on modernized version of existing software uh, is, strictly speaking, is not innovation. So, of course, you can write 1 or 2 papers on your code on your software, but uh, it's difficult to produce reasonable amount of papers in these 3 or 5 years. So it will be difficult to persuade the students. Even if I could persuade the students, I suppose my university would not allow me to do this to the students. And of course, if I started working on it today, then the story would be completely different or quite different, because today we have powerful AI to especially for coding. But even first in 2020, we didn't have this tool yet. Secondly, even with the AI tools today, if we just give them the 8,000 lines of Fortran 77 code with 250 go-tos, uh, I'm not sure how how good AI will be able to translate them the code into modern a reliable modern implementation. Of course, AI will give you quite good looking code, and the code will even work in most test cases. But I don't think we can give you a piece of code that is guaranteed to be a faithful re-implementation. And also, there are many edge cases. Even for AI, I think it will be difficult to find without really extensively test the code. But with a modernized implementation that is modularized, all the 3 points here will become quite possible. For example, I can hire an engineer to implement Power's code into any language that we want, based on modernized and modularized implementation. I can also find a student to work on it. In fact, currently I have a master student who is exactly working on Power's algorithms based on the modernized reference implementation that I have. The work I give to him is not to re-implement again the algorithms, but to write a translator that can translate the modernized reference implementation into any language that we are interested in, for example, MATLAB or Python or Julia. And the requirement is that the translated implementation should be for humans, should be friendly and also readable. It should not be just a piece of code for machines. And I asked him to write such a translator. It is possible because uh, if you look at the modernized reference implementation, you will find that the code is quite close to, for example, MATLAB, because the syntax of modern Fortran is almost the same as MATLAB. It supports, for example, multi-dimensional arrays, or in other words, it supports matrix vector operations naturally or natively. So it's doable to translate the code using some automatic translator. That's what I'm asking my student to do. And of course, we can we can use also AI to translate this modernized, modularized implementation. Um, I'm sure that AI can do a good job. But the reason that I don't use AI but use my student to write such a translator is that I still hope that the translator and also the translated code is is reliable up to a very high confidence level. So I don't for the moment I don't trust so much the code by AI. Maybe I'm too conservative here, but think about the applications of this code. People use it to design aircraft. So, for example, so for these critical implement applications, we hope that the code is highly reliable. So that is why I didn't use AI to translate the code. So this is the software package that contains the modern implementation. It's called Prima. Lina also mentioned it, and I worked on it for 3 years during the COVID time. Uh, the current version it has not incorporated the translator and also the translated code yet. It contains the modern Fortran implementation and some interfaces to C++, Python, Julia, and MATLAB. So if you are interested, you may try it. And I hope that within 1 year, we can also add the translator and also the translated code to native Python, Julia, and MATLAB. Yeah, just I think we need to be fast, so I will skip this part. So Prima has replaced Power's Fortran 77 version of Cobila in SciPy, starting from SciPy 1.16.0. Yeah, this is my work about on Cobila. On Prima. And we also got some feedback from industry. In fact, Airbus is now using the Prima version of Cobila in their aircraft applications, and they found that the new implementation works quite well. In fact, according to the engineers, the new implementation works evidently more efficient than the old implementation, and also it works quite robust in presence of noise. I'd like to also mention very briefly my work with my PhD student, former PhD student. Another piece of model-based DFO algorithm, POVQA. So it is a power style model-based SQP algorithm. Power style means that we build models, quadratic models for the additive function and for the nonlinear constraints using Power's way of building the underdetermined quadratic models. So and the outer the global framework is SQP framework. We're not here it is a very brief introduction about this algorithm. So the classical SQP is to build a quadratic model for the Lagrangian of the problem, and then linear models for the constraints. And if we have derivatives, of course, the models would be based on the gradient information, and sometimes even the Hessian of the problem. But we don't have such information, so we build quadratic models and then replace for example, the gradient of the ablative function in the SQP ablative by the gradient of the model, and so on. And CoBQA is now also in SciPy, so it has been incorporated since SciPy 1.1 4.0. This is not the end yet, but I would like to first thank you because when I was working on especially on Prima, it took a lot of time, and consequently I didn't have time to write papers because I had to concentrate on this work for 3 years. So really, during these 3 years, I didn't write paper. I didn't do anything except for coding and also supervising the PhD thesis or of course teaching. Of course it has some impact on the on your I mean on my career. So it was not easy, but finally I survived. So this is not possible. This would not have been possible without the support from the community. So I'm always grateful for this. Yeah, even though a big part of the support impact is unknown to me, but I'm really grateful deeply in my heart. Okay, now let us talk about Yuan Stewart. So even though I spent a long time on Powers methods on Prima, but it's not my work. It's Powers' work. My work is just to maintain and to improve a little bit. And no, I don't think we should stop here. And also, even though Powers methods are powerful, uh, we should not regard them as the best method. Otherwise, I don't. If Power knew this, he would not be happy because the 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 spirit of research is to always find better outcomes, right? So I hope that the work on Prima paves the way for developing new and better DFO algorithms based on the treasure left by Power. And now I will give you such an example. This example, in fact, is not quite new. It's quite old, but the methodology behind it becomes quite popular recently in the DFO community. It is the subspace methodology. So that's why I choose to talk about it today. So in our DFO community, there have been or there was a belief, a common belief that we cannot solve big problems. For example, in this award-winning monograph, the authors, Andy Cohn, Katja Schamberg, and Louis Suissant, they mentioned that the DFO algorithms cannot solve problems with more than a few hundred of variables, even in the easy cases. Of course, we have to be careful because this comment came from this book, which was first published in 2009, so 17 years ago. So this is a very old piece of comment. But very recently, I think 2 years ago, more than a year ago, I visited Toulouse, and I had a conversation with an engineer from Airbus. He mentioned that he was working on some DFO problem. So I asked the dimension about the dimension of the problem. He said that it was 3. And I asked why the problem is so small. He said that in fact we have bigger models, but since you guys cannot solve big problems, so we design the models. We always try to make it as small as possible. So this means that the belief is not only within academia; it also has in fact affected industry. And this becomes a loop of negative feedback. So we have to ask whether this is a myth or truth. So can we solve large problems? Of course, in recent years, or at least in recent 5 years, in our community, there have been a lot of work on large problems. And now we know that the DFO algorithms of course, can solve big problems with some techniques. One of the top techniques is subspace method. And here, I first give you a table of numerical results where I compare two algorithms. One is called, I call it NUUAS. So NUUA is the name of the Power's unconstrained solver without using derivatives. And there is a small s. The small s, in fact, I put it in the name to indicate that it is a subspace method. But it is not a subspace variant of NUA. It is NUA and subspace. Yeah. But even though that this is only a small s, but it's in fact a major part of this algorithm. And the other one is FMUNC. It is a built-in MATLAB function to solve unconstrained problems. If you don't give it derivatives, it will do finite difference PFGF. So as we can see, the result given by NUAS is much better than the result given by FMUNC, the function values. And another point to mention is that the function values here have only three correct digits. So it means that the solvers, they receive noisy function values without knowing it. So they thought that the function values were correct, but in fact, only three digits of them were correct. This is the NUAS algorithm. Of course, I know that most of the audience cannot read Chinese, but here I present a screenshot because it's part of my PhD thesis dates back to 2012. I put a screenshot here just to let you know that it was like this in my thesis. Even though you cannot read the Chinese, but you can read the equations 5.59 and 5.60. 5.59 is to design a subspace Fk. This Fk consists of two dimensions. One of them, GK tilde, you can imagine it is approximate gradient. And Fk minus 1 is the last step of this algorithm. And later I will explain why we design this subspace in this way. And then 5.60, it is to restrict the problem on this subspace and then solve it approximately. And here, even though the problem is restricted on a subspace, it is still a derivative-free optimization problem because we don't have first order information of f. So we can solve this problem only by DFO algorithm. That is why I needed NUA here. So here we talk about unconstrained problem. So it is an unconstrained, low-dimensional derivative-free problem. So I called NUA to solve it. So these are the two components of NUAS. So here is a framework that generalizes or that is underlying this new algorithm. This framework, of course, is not by me. Here I refer to a tech report by Kong, Tuan, and co-authors. But in fact, I think this framework existed even before that because it's a very classical one. So first you pick a starting point, and then at each iteration you build a subspace, and then you restrict your problem on this subspace, and then you solve your problem approximately and then iterate. This algorithm, this framework, even though I describe it for unconstrained optimization problem, in fact, I claim that it can be used to solve any optimization problem, or even any scientific computing problem. So you just design a subspace and then somehow define, restrict your problem on this subspace and then solve this subspace subproblem approximately and then iterate. The question to answer is how to design this subspace. And also on the subspace, can you solve the subproblem efficiently or not? As long as you can answer these two questions, then you have a subspace algorithm that is good for your problem. To answer these two questions, we can analyze this subspace framework roughly. And in fact, it's quite easy to prove that uh, uh, to make this framework convergent, you don't need first order information. What you need is approximate first order information. Or in other words, as long as your subspace contains an approximate gradient, and as long as you can solve the subspace subproblem sufficiently exact, then the algorithm will converge. In fact, it's quite easy to prove. This tells us that we don't need first order information to implement this framework. What we need is a model that provides us with approximate gradient around the current iterate, and also a good solver to solve the subspace subproblem.
Zaikun, we've got maybe
Then
1 or 2 minutes. Sorry.
Okay, then I will speed up. Yeah, then how to design this subspace? I refer to classical work by Yuan and Stewart from '92. So the subspace contains two dimensions. One is the current gradient. Another one is the last step. The last step, of course, these days people call it a momentum step. But in their work, they didn't call it in that way. Their motivation came from the conjugate gradient method. So the conjugate gradient method, the conjugate gradient direction is a linear combination of the last step and the current gradient. So it is in this two-dimensional subspace. And then the to implement it without using derivatives, then we just need to replace the gradient direction using approximate gradient direction provided by some kind of model. This model can be any model that you obtain using implementation using interpolation or finite difference or any other kind of methods. And here I give you there is a short note I wrote last year about this framework and also this algorithm. It is, of course, in English. If you're interested, you can have a look. And then, yeah, I will skip this. Is some analysis about this algorithm, and you can find the details in the short note. And of course, I have to mention that Linden and also Cora also worked on subspace methods on model-based DFO. But if yeah, we made some comparison with Linden's work in our note. And this work was used in Intel for designing chips. And yeah, in fact, the product was released, I think 2 or 3 years ago. It was Atom P5900. Initially they used NUA to solve the problem, but it took weeks for them to solve the problem. And finally they used NUS. It took only several hours. And it was also included in Intel's this toolbox for designing chips. Okay. Finally, I mentioned briefly optimist. So the idea is to go from unconstrained to constrained optimization. Of course, you can use penalty, you can use augmented Lagrangian, although also you can use some recent technique called constraint dissolving. But we would like to think about it, the constraint case directly. So here I give you a framework. It is essentially the same as the framework I mentioned before. The only difference is that when you solve the when you design the subspace subproblem, you also take into account the constraint, and which means that you don't solve the problem in the subspace, but the intersection between the subspace and the shifted version of this physical region. And but the problem is how to design the subspace. Due to the time limit, I will not talk about this part, and it's also work ongoing. So I will skip the details, but I just mentioned that globally we the idea is the same as new US. So we design a subspace, and then in the subspace we have a low-dimensional DFO subproblem. We solve it by Prima. This is another reason why I worked on Prima for so much time. And then I conclude. So as we already know, DFO is an exciting research area, and And to solve large problems, we can use subspace method. Of course, we hope that the techniques of subspace can solve us to scale DFO algorithms to, for example, thousands or tens of thousands dimensional problems. And then also I emphasize that DFO methods needs good software packages, and this takes time. And hopefully that the new AI tools can make this kind of work easier. But still, we cannot omit this part. So yeah, that's all. Thank you.
Okay, thank you so much, Zaikun. I'm conscious of time, so if people have to run off, please do. But hopefully we can stay on for a couple of minutes for questions if people have anything they want to ask. Zaikun,
Yeah.
so
I'm happy to answer
put things
questions.
in the chat or raise your hand or anything if you do have a question. Check. We don't. I might just jump in then and ask, with this sort of subspace method, I guess if we're looking at
Yeah,
AI ML applications, they like to do their gradient sampling, they kind of randomized finite differencing.
yeah.
Does that give you a good approximate gradient for something like new UAS?
Yeah, that's a very good question. In the current in the framework that I presented, no, but this just means that the current theory does cannot accommodate this kind of randomized approximate gradient. But we can, of course, we can extend the current framework or the theory to use this kind of approximate, randomized approximate gradient. I think it aligns somehow with your work on randomized subspace method.
Yep.
Yeah.
Okay, great. Are there any other questions before we wrap up? Okay,
I
if
just wanted
not,
to say how
oh,
impressive that is. 3 years
Thanks, Scott.
of coding. That's
Yeah,
also my worst nightmare.
but at least in 2020, even now is for sure that this kind of work is needed. But
Yeah.
the story would be different if I starting now, because the AI, even though they cannot handle such complicated code base directly, but they can be quite extremely helpful. But when I was working on that, I did everything manually, and I know that Linden also did the same work on one of the algorithms manually. So yeah, Linden can also uh, share the same feeling, I suppose.
Can I just ask subjectively, how do you feel about that? Is there a part of you that's like, oh, if I had just waited 5 years, this would have been so much easier? Or is there a part of you that's really glad you did it because you can now say you've done this really difficult thing? And you also know you've looked at every single line yourself. I mean, how do you feel about it now?
Yeah, yeah, that's the question. Um, it's mixed, both. Yeah, part of me, feel that feel lucky that I did it. Part of me would prefer that I didn't need to do it. But of course, in this first in this process, I learned a lot. I learned a lot about these methods, and also learned a lot about the power. Uh, but yes, it took too much time, and it was quite painful. And but the happy side is that it's useful. People are using it. And if
Yeah,
I
it looks like it's
didn't,
got hundreds of
yeah,
stars on GitHub. It's
yeah,
clearly
yeah.
getting attention.
Hmm. Hmm.
just to flag the amount of attention to detail that Zaikun was putting in, I was checking the source code to check a specific technical rule that I mentioned yesterday of if you're
Uh-huh.
replacing, if you've got to had a successful step and you want to update your model with that step, which point do
Uh-huh.
you remove? And I mentioned there was like a
Hmm.
distance criterion based on Lagrange
Yeah,
polynomials. I had a
yeah,
look at one of Zaikun's codes, and he had tested for that one line of code approximately 10 to 15 different variations of the formula for that one line
yeah.
of code. That's how thorough this work was.
Yeah, I know
Um,
which part you meant. Yeah, I remember that I tested many probably possibilities. It's because if you look at Power, because Power had five of these solvers. So for this particular part, he had at least five different strategies. And in that particular solver, he used only one of them. But I was not sure whether the others would work better. So I tested all of them. And also I had my own variant. So yeah, it was. I mean, I hope that what I did was useful, and also sometimes it improved the solver. Yeah.
okay. Well, in that case, I will say thanks again to Zaikun, and I will stop the
Uh,
recording now.